and more and more non-overlap wouldn't increase this measure. But I think that's a relatively minor drawback in most cases. I haven't seen non-overlap in a lot of studies. A couple of those that Rob showed just before the break were non-overlap. You saw some of those baselines of zero, of no behavior, and then a change to behavior. Those, it would be difficult to use this kind of a measure on. So what I want to do to create this better non-overlap measure, not a perfect one, is put the vertical line where everybody does between the phases, and then put the horizontal line so that you cut into the same margins. Like we had 6 people in the base, 6 observations in the baseline and 7 in the treatment section. And so we want 6 below the horizontal line and 7 above, if it's possible. There's a possible problem with tie-scores, which we ran into in that example, and you can put half one place and half the other. But in one thing we don't want to use, as in some of those measures, is the median of the baseline phase, because that automatically makes it tough to get a perfect measure, because automatically half are above in the baseline phase, half are above the median, and half are below. And then I just want something that's based on the number of points in each cell. Since you're not statisticians, I won't tell you about Hedges and Olkin. I'll show you this picture again. We want to if these are standard normal distributions with not standard, if these are normal distributions with standard deviations of 1, then the distance between this peak, where this peak is, and the distance where this peak is, right, these happen to be, for this example, these happen to be a z of -1 and a z of +1, or where the means are of these. I want my measure to measure the difference in distance between these 2 points. The problem is we don't have those. We don't have these distributions, right? What we have are how many people are above the median in each group. So that would be the area under this curve over here, and the area under this curve for the other condition over here. And then how many people are below the median, and that would be the area under this curve for the one condition, and the area under this part of the curve for the others. So I figure how many people, if I told you a z-score, would be able to figure out the proportion of people above or below that z-score using if I gave you a table, right, you'd be able to look it up and see what are the proportion below here, what are the proportion above here. That's the area under those curves. So I figure most researchers, if they've had a little introduction to statistics, can do that. And that was actually that fancy equation at the bottom of this page. Phi inverse of P is figuring out the z-score, the area under the curve above one place or below the other. And that is equal to the distance in z-score units between the baseline phase and the treatment phase. Now, it's easy to understand what the area under the normal curve at various points is. Everybody learns that in their first statistics course. And it's easy to compute. You got lots of ways to compute it. The standard error is harder to compute, so I wouldn't want anybody to have to do that. So I found a solution to the problem, which is that the logit and the probit are very close to each other. If you ever seen, well, for those of you who are specializing in stat, you know the logistic curve and the integrated normal are close, except they differ, their standard deviations differ. That's why in an IRT model you have 1.7 as a factor and one and not the other. The rest of you people, forgive me for saying all that for just a minute. Just wanted to talk to a few people who really are nerds like me. But the thing is, I can teach you how to use it even if you don't understand what it means. If you ever did an analysis of 2x2 tables, which is the simplest kind of analysis there is in categorical data, it's often the relationship is expressed as a difference in the log odds ratios. And so it's the log of these A, B, C, and D are the cell frequencies in the 4 cells of the table. And the nice thing about this, I mean, if you can press the log button on your calculator, you can calculate this, so that's not too bad. You can't do it in your head, but you could do it with a simple calculator. The nice thing about this is the standard error is simple to get. It's the square root of the sum of 1 over the frequencies. So 1 over A plus 1 over B plus 1 over C plus 1 over D. And there are problems with cells with zeros, as you techies know, so we add 0.5 to the cells to solve for that. And to give you an example, I took this picture from the bigger figure that I gave, and I didn't redo these tables to really correspond to the exact, to where I really want the horizontal line. I want it down a little further to be right, but just to show how the calculations are done using one of these tables, I created a function to do it. That's enough of the function. Okay. All I have to do is take the frequencies in those in one of those tables, 0 in one cell, 5 in another cell, 6 in another, and 2 in the other, and put it and give it to my function, non-p, for a non-parametric p. And it'll print a bunch of things, the most important of which are down here at the bottom. Whoops. Most important of which are down here at the bottom. The first one, which says difference in phi, that's the difference that I would have liked to use because it's conceptually right. But instead I used the log odds ratio adjusted by a factor of 0.6, so it's 0.6 times the log odds ratio. And I put these two here next to each other to show that my simple method is about the same as the more complicated method, which you have to find the area under the curve, and that I can get a standard error for that. And therefore, if I want a confidence interval, I can get a confidence interval on that. And that's really good. Again, as long as, a caveat, if the points don't overlap at all, you can't determine how far apart the groups really are. So, but for many reasonable values of that are in these tables, you can get an estimate, you can get a standard error. This will allow you to do things in comparable units, although the meaning of an effect size in a single case design is different than the meaning of an effect size in a group study. Because in, let's go back to these plots. In one of these, you're comparing the difference in the mean for one phase to the mean for another phase, and essentially dividing by the standard deviation of a person's behavior across time, a single person's behavior across time. This is like looking at the signal to noise ratio. You may have heard, you may have seen Nate Silver's book, The Signal and the Noise, about separating out what's really going on from the noise in the background. This is what's going on here. The noise is individual variation from time to time within a phase. Why does a person behave differently from one session to another, even though nothing's being done to them? Nothing different is being done to them. These are the things that Rob talked about as being so important to look for in single case designs, because you don't want something that's varying a lot over time before you do anything. You want it pretty steady. That's the only way you can make the signal stand out from that noise, is not to have a lot of noise in the first place. And that's one of the things that's supposedly good about single case designs. But if you look at a lot of the graphs, they're not so well behaved. Now, Rob has some nice examples of well-behaved data. I mean, those ones I saw, that last one or two before we took the break, with a baseline flat, where the person's not doing what they're supposed to be at all, and then you get treatment and they're doing it, that's a great demonstration. That's beautiful. That's the way you want it to be. But I bet he had to look long and hard to find that example, because I've looked through a lot of books and journal articles to do analyses, and I wanted nice, simple things to demonstrate with, and I had a terrible time finding beautifully behaved data. So if you think of all these methods that Parker and his folks have looked at, there are some of them that are better than others, but most of them don't have a quantity that they're estimating, a parameter that they're estimating, and some of them are subject to really very basic problems, like the one where you divide at the median. That's a very basic problem where you can't have, you force half the observations to be high and half the observations to be low in the baseline phase. And there are others that have more subtle things, like even if the one where you pick the high point for a dividing line. You know, it's obvious there's a problem if there's an outlier, but even if there's not an outlier, there's a problem with that. And it's the same problem with the range. You're all taught in statistics what? You look at the range as a measure of variability, right? Do you know what quantity the range estimates? What in a population does the range estimate? What are you estimating when you estimate the range? Or some function of something. Even if it's a normal distribution, so it's a nicely behaved distribution. What does the range estimate? The answer is, it doesn't estimate anything. The range is a number that is very problematic. And you can see it just by imagining. Take a sample of two points from a normal distribution. They're, say, where my left and right hand are. Right? That's the range, is the difference between those two, because you only got two numbers. Now take a third number. What can happen to that third number? It could be between the other two, in which case the range doesn't change. Or it could be above the high one or below the low one, in which case the range would increase. Okay, so now it's here. Now take a fourth point. It can either be within the range already described, or it can be higher or lower. So it gets bigger. So the range, as the sample size gets larger, the range is expected to go up and up and up and up. Right? So it's not estimating anything. Therefore, anything based on the range or a high point or a low point of something, even if there were no outliers, there's a problem with that. It's something that I don't think is taught in very many statistics books, but you got to be cautious of things like that. That's what you need statisticians for. That's what I needed a statistician for, because I didn't think of that myself, believe me. It's something I read, I can't take any credit for it. So there are all these things you have to watch for, but you can still, now, my method still requires a little calculation. It still requires a little understanding, but it's a lot less than the things I'm going to show you, right? So I guess that's a sad thing to say when something that seems complicated to you is the simple thing compared to what I'm going to show you. But it is. So that's, it renders this single case design measure comparable to D, except that it's for individuals rather than between individuals. And when you look at the What Works Clearinghouse, which I think Rob mentioned a little bit, you have to satisfy them that you've done things